We're going to jump into the next technical topic here. And I got elected to speak on it. So we're going to talk about ET. Okay. Evapotranspiration. And we're going to wait till John's done, but we're going to try to go through ET actually fairly quick. ET is fairly physical in nature. There's a lot of computations to get into ET. So let's think about this from a hydrology aspect. We're going to, as we're doing this, so when I work with, like when I've taught classes, I like the whiteboard, and I know that there's people online that can't see. Can the people online see the whiteboard? No, they can't see the whiteboard, can they? Okay, so I'm sorry for the people online, you can't see the whiteboard, but I like to use my hands and I like to draw because I'm still a young kid who likes to draw, okay? So I'm gonna draw. So primarily to take notes, but if we're talking about hydrology, you know, everything in hydrology is connected, right? So in hydrology, everything is connected. Why do we talk about ET when we're talking about hydrology? Oh, sorry, yeah. Why do we talk about ET, evapotranspiration, when we talk about hydrology? Okay, and that's the question I'm going to ask you. What is ET first? Does anybody know what ET? Do you know what ET is? You know what ET is, right? Evapotranspiration, right? Okay, it's evaporation and transpiration. Okay, so, but why is it important? So there are many parameters that are important into hydrology. Is this covered under a slide? I don't even know what's on my slides. Hit the next slide. Or is it? Where's my slides? Oh, you do it for me. Okay, so the parameters that are important in hydrology, I mean, there's things that we study in hydrology. When a lot of people think about hydrology as stream flow. Okay, but yeah, stream flow, you know, we have models that do that. You know, when the water gets into the stream flow, we have, you know, the overland flow, you have time of concentration, all of those variables, right? You have surface roughness. So you have your land use parameters, you have your soil moisture, that's part of hydrology. You have, in order to figure out stream flow, you have to go through each one of those parameters and figure out how to, you know, how does the water get into the stream? So there's a soil moisture, how much water is going into the soil, how much water is going into the plant, okay? And then, you know, how much water is going to your deeper part of your soil, okay? So I mentioned plant because plants, you know, provide both an intercept as well as a capture of your water. Okay, so you have the root zone soil moisture, which is really important, what we call the root zone soil moisture. That's part of hydrology. And then we also have, you know, the deeper groundwater. Okay, and when we're talking about surface hydrology, the groundwater is actually a lost term because it just disappears in a lot of our models. Sometimes we put a groundwater model in there, sometimes we don't. Okay, but this root zone soil moisture is a key part of most of our hydrology, surface hydrology models and land surface models. Okay, and the reason the root zone soil moisture is important is because in these land surface models, we have vegetation. And the vegetation is also a lost term for water. Okay, and I call it a lost term because the water is not going into the stream, the water is going into the soil, and then the water is going through the soil and the plant is coming and picking it up and putting it, you know, into the plant to help keep the plant healthy. Because what happens when that plant doesn't get water? It dies, right? So, so the uptake of the water into that plant becomes important. And what kind of governs that process? You know, how much water is going up into that plant and how much water is then, you know, when you have a big plant, this is the ground, and you have a plant, you know, a nice big tree or something like that, and you have all the root structure, the water, you know, this plant is taking moisture, it's pulling it up into the top, it pushes the water into the canopy, okay? And then that plant breathes. So that's the transpiration part. And that's governed by a number of processes, all right, which we can somewhat predict. Okay, so that's the transpiration part of it. And the rest of the term is simply the evaporation off the surface. So when the sun is up and it's radiating on that surface, you have an energy that's intersecting with that surface. That energy is converting the water that's in that surface through evaporate, it's evaporating the water off that surface, and then that energy then leaves the surface, and that water is no longer available to stream flow. And if we're going to model hydrology accurately, we have to be able to cover this part of surface hydrology, okay? Because it impacts our ability to estimate soil moisture. It impacts our ability to estimate stream flow accurately. And if you're interested in drought and drought impacts, that you want to be able to estimate, essentially how healthy is the plant by looking at things like how much water is available to the root of your plant. Okay, how much water is available to move up into that plant? Can you measure the transpiration or the health of that plant remotely, okay, from satellite? And if you can measure the health of that plant remotely from satellite, then you can then use that to go in and update your model, or to get a good understanding of, are the crops growing well in this area because the crops look nice and green, or there's a lot of, we measure soil moisture. So therefore, because there's a lot of soil moisture in the root zone, the crop should be healthy. Okay, so, countries, farmers, agricultural groups around the world want to know this root zone soil moisture, the health of the plant, and and they use what we call the evapotranspiration parameters to help with the health of the plant, as well as to understand the amount of energy that's being exchanged between the land and the atmosphere. Okay, so the water that comes off this plant goes to the atmosphere. Okay, and the water that comes off the surface goes to the atmosphere. The more water in the surface, the less energy through sensible heating, and the more energy through latent heating. Okay, so that's why transpiration becomes really important. Hit my next slide. So I'm going to go through this slide. So we've actually essentially gone through this process. Okay, so I've totally gone off the rails on this, haven't I? Oh, what's the next slide? Okay. All right. So there are a number of ways we can measure, we can assess essentially the evapotranspiration. Okay. There are models. There are remote sensing methods, and basically models and remote sensing methods. One of the most common model to try to estimate that evapotranspiration firm, or the what we call the reference ET value, is this equation called Penman-Monteith equation. Okay, it's a long equation. So we have land surface models. I run a land surface model called the NOAA land surface model, and there's like 3 subroutines in that model that just deal with the Penman equation and the bare earth evaporation. Okay, so if you have, oh, here it is. You're doing good. You just keep evaporating. You just keep advancing this. But so this is the Penman equation. And so you need a number of parameters. Okay. And these parameters are not things that you can just go pull out of, you have to have like a full weather model to be able to run this. So these are fairly complicated things. All right. So the flux, the ground heat flux, anybody know what what does that mean, ground heat flux? Anybody want to volunteer and say what they know what the ground heat flux is? That's the flux, that's the amount of energy that's being stored essentially down in the ground. Okay, so when the sun comes in and it warms the ground, okay, not all of that energy is then converted and re-rated back up. There's a warming of that surface, and so that's the ground heat flux. Okay, so we need to know the ground heat flux variable. We need to know your vapor pressure deficit, the net surface radiation, how much energy is coming in from the sun. So you need to know cloud cover. You need to know time of year, what your solar angle is. you need to note the air temperature. There's some constants in here. So there's a latent heat constant, a specific heat constant. So there's a number of constants in there, and those values don't really change. But the dynamic variables are the ones that are important, okay, to be able to run this and generate evapotranspiration. Okay, next slide. Okay, so one of the ways that we can get at looking at evapotranspiration is by looking at essentially a crop health parameter. Okay, so it's based on an NDVI type relationship. So there is a direct relationship between some of these crop coefficients and the NDVI. And so you can get at essentially your evapotranspiration parameter by looking at those relationships. And some of this data is available from MODIS. And so what we're going to do in about 10 or 15 minutes after I get through this part of it is we're actually going to give you a couple of examples of grabbing some of these parameters from MODIS and looking at, because they're already computed. The nice thing about MODIS is, we've nested some of these parameters as remote sensing algorithms already in the MODIS processing. And so you can just go download it. And then we have a Google Earth, is it a Google Earth engine kind of demonstration we're going to run through? Is Sean coming up here to do that, or are you going to do it? You're going to do it? Okay, you're going to, really? Oh, wow, okay. Good. So, okay, next slide. Okay, so let's look at some of the products. I'm going to put this down because I'm dangerous. So there are a number of models that you can get that actually compute this, that have the full set of equations in them. All right, so the one that actually is the most complete is the GLDAS system at the bottom. And this specific link actually links to NASA's GLDAS website. Anybody ever hear the term GLDAS before? Well, other than the NASA guy, come on, Sean. Okay, a couple of you have worked with GLDAS. Okay, GLDAS, Global Land Data Assimilation System. Okay, John touched on assimilation yesterday a little bit, but GLDAS actually runs, inside of GLDAS, we run land surface models that have the full Penman-Monteith or other, some of them are so complicated, they'll run a full dynamic vegetation model inside of that to look at how much carbon, is within the system. Okay, so they can be quite complex, right? Alexi, this is a remote sensing based system. And metric is another system. And so the links for these tools and the products that are generated are on this slide deck. Okay, and you have access to this slide deck through the GitHub system. So you should be able to, if you want to go browse some of these sites, you should be able to go browse that. Each one of these is a bit more complicated than just looking at like a pure remote sensing product. So what they'll do is some of them are like Metric and Alexi are combining remote sensing products with a model. So instead of a model pulling in a remote sensing product to generate the product, those are more it's a remote sensing product combined with a model. So it's a little bit different than the pure modeling approach. Okay. Next slide. These are other systems that you can go take a look. NLDAS is the same thing as GLDAS. We just put a different letter on it because it's for a region. Okay, so North American Land Data Assimilation System. If you developed an LDAS for all of South America, we could come up with a brand new acronym and we could call it SLDAS, which doesn't exist yet. Somebody tried developing that a while ago, but it doesn't run. But that could be possible. We'll develop an SLDAS for all of South America, and we'll add another link down here. Okay. Yep. So those are some of the links. There's some Africa stuff. Each one of these has a number of satellite products that go into them. So GLDAS pulls in both the precipitation as well as the land cover products from multiple satellites and the topography. Alexi has, again, a bunch of satellite data that goes into it, right? But again, to do the full complex ET product, you can't really do it. You can't really get to it necessarily from purely remote sensing it alone without heavily parameterizing it. Okay, so that's why these are all really heavily model focused. And then on the Google Earth Engine, you have the metric system. Next slide. Okay, and so the applications, I've already gone into the applications of ET a little bit because I've kind of gone through this backwards. If you have ET values, or if you're looking at different crop parameters, then you can remotely assess crop health from space, either using NDVI or some of the evapotranspiration remote sense products. The US regularly does this, especially for US, US areas. Will come in, the US Department of Agriculture will come in and they'll remotely assess crop health from space using NDVI and some of these other model-based products to basically say, okay, we think the US crop, of a corn crop or soy crop or other plants are really, really healthy in the eastern half of the US because it's been quite wet over there, but out, west in Nebraska, they've been going through a drought. And if that's the case, then they'll send people out there to take it, to go observe it. And then they, the USDA then does kind of this crop production estimate. And they use these products directly in their crop production estimates. So it's an agricultural, based product. They use soil moisture, they use the vegetation products, and they use the ET maps, okay? You can also get a really good idea if somebody's irrigating or not by looking at that. If you run a model, and this is really cool. If you run a GLDAS system like I do, the Global Land Data Assimilation System, where you're trying to remotely predict or assess soil moisture using a model-based system, you can compare your estimate to the satellite data. And if you have a very, very big difference between your model estimate and the satellite estimate of like crop health or soil moisture using the satellite products, then you get a really good understanding of who's irrigating and who's not. And then you can try to add some of that those irrigation parameters back into your model. Okay, because our models predict, how healthy the plants are going to be because we have ET in them. And, we can then come in with from satellite and say, okay, how well is our model doing? If the difference is really big, then it's a pretty good idea that they're irrigating. So, okay. In the US, we get a really good estimate of, how well our, what we call our agricultural drought. So there's three types of, drought, right? There's groundwater drought, surface hydrology drought, and then an agricultural drought. So if your plants aren't doing well, then you can have that agricultural drought, and you can measure that crop health from space. Okay. This is another water allocation irrigation thing. You can measure. Is this Landsat? Well, this is metric. So this is a metric chart. Looks like probably for some Western US area. Notice, because we're measuring this from space, there's a bunch of little circles through there. That's pivot irrigation. So we're getting a really good idea with this product on where people are irrigating and where people are not. Everybody know what pivot irrigation is? I get some confused space. Okay, pivot irrigation, what pivot irrigation. Yeah, so it's irrigation systems based on a pivot. And so you have this big arm that basically pivots around a center pole. Okay, there's a big company up in Nebraska that sells them around the world. But those pivot irrigation systems create a very, very nice crop circle, if you're looking at the irrigation maps. Okay, and easily visible from space with these types of products. So who's irrigating and who's not. And even based on the value, like the depth, of the product that you generate with these, you can figure out essentially how much they're irrigating, or, if they're irrigating at all. Okay, so that gives you that value of the amount of irrigation that's happening. And you can tie that back. If you know how much they're irrigating, you can, and you know, whether or not it's legal or not, you can then even go back and look at, you know, where's the water coming from for that irrigation and really tie it to a water resource perspective. Okay. Yeah, so the water, and that ties it into, you know, the water allocation for irrigation. So, you know, that goes back into the planning aspect and the, you know, the regional considerations. So again, another product for planning, and then, you know, you could tie it in Nebraska. So since I used to live in Nebraska, I'll give you a story about Nebraska. So Nebraska for years was illegally using water out of a river system for irrigation for their Western crops. So even in the States, we have these trans-state agreements for water sharing for the different river and even some groundwater systems, because we have shared aquifers, we have shared rivers. And so one state in the US, Kansas, sued Nebraska over water rights because they figured out that the Nebraska farmers were pumping too much water out of the ground, out of both the aquifer and the Republic River, and using it for irrigation. And well, that was stealing money, that was stealing water from Kansas and from the aquifer. And that aquifer, the Ogallala aquifer, you know, stretches from basically Colorado to South Dakota, Kansas, or Nebraska, Kansas, and eastward, and it provides water for a lot of people. And so because of those shared resources, you can come back in, you know, look at that not only the irrigation from space, and then you can somewhat measure, you know, the drop in both the, you know, the water from a stream flow perspective and others, and then you know, make assessments. I was a taxpayer in Nebraska, and Nebraska lost the lawsuit, and so my taxes were directly affected by those farmers. And I had to help pay the bill, which, you know, that was, you know, it was $100 or something like that, right? So anyway, next slide. And I think what we're going to do now is, so those are the impacts of ET and how we can use ET from space. So I want to go into the demo now. So why don't we, so did you put that file? So no, what we're going to do is we're going to give you a demo of how to pull the Modus ET product down from the web page, and then to just put it into QGIS. So that's the first demo we're going to run. Okay. So how to go get the Modus ET product, pull it down, throw it into QGIS and look at it. And again, it's on a tile. And then the second thing we're going to do is run the Google Earth Engine. So we put some simple instructions up. Did we put that online? So we have some simple instructions up. And he's pulling them up right now. Okay, here's the instructions. This is an easy demo because you go get the data, and here's the website. So he converted the website into this really, really short a bit.ly link, right? So it's a bit.ly link. So if you copy this website address into your browser bar, okay, you should be able to get to the website that has the download for the Modus granules, okay? So, and we're going to do that in just a minute here after everybody copies that website down. Okay, so that's the download link. All right, so do you want to try, do you want to go to, click the link to go to the download link? Everybody have the link? Okay, so this, what was that? Okay, so that link leads you to this page. All right. Question? Somebody had a question? The link again? He needs the link again. He didn't copy it. Okay. Just show this page. So it's, it's the HTTPS bit.ly/3 capital A small g 6 capital R capital N capital K. Okay, got it? So if you get that link, that brings you to, it's a USGS web page. So again, NASA and USGS both host a lot of this MODIS data. All right. So when you get to this page, if you signed up for that Earth Explorer account, that will enable you to download data from this site also. And this is actually a bit more of a direct. I like going to this site because I can write a script to go here and just automatically download the data. Okay, but what we're going to do is we're going to search. So each one of these files here is a MODIS granule. And that MODIS granule is just a section, it's not the entire global data, it's just a section of MODIS data representing, a regional area. Okay, so the granule that represents parts of Argentina, and that we're going to use the Argentina granule that I found. The entire world's in there, but the Argentina one is this middle section of the MODIS file name is the granule ID. Okay, so if once you memorize the granule ID for the area you're interested in, you can search for that granule ID. The parts of Argentina and southern parts of Paraguay and stuff are H12V12. Okay, H12V11 is just above that, so that's parts of Paraguay and others. But I want the H12V12, and so search for H12V12. The mod16A2 file, which is the specific product that we're going after, the H12V12 file, and the HDF file. Because HDF is the file that goes straight into your QGIS. Okay. So if you click on that link with your and then enter your Earth Explorer password in, you should be able to download it. Okay. You have your, okay. So we're going to go ahead and just go and pull that file into QGIS just to show you how easy it is. So if you open up QGIS, here's QGIS. Again, drag and drop. So pull that file in and just drag it in and drop it. Simple as pie. I wish doing GIS was this simple when I was in school trying to learn it. It was not. Okay. There are 5 different products within that file. You can load them all in. Yeah. Anybody have any issues getting, any questions going on? Everybody able to download the data? Anybody try it? Anybody try it? Anybody successful? Did you get it? Hey, 1 success, 2 success, 4. We got 4. Okay, good. Everybody else? Anybody else successful? Okay. Who's having troubles downloading the data, or who's just stuck? I think most people are able to get it. Okay. Good. If they signed up for the Earth Explorer account, then they should be able to use this account also. The Earth Explorer account yesterday. Okay. Okay. So when you pull those into QGIS, everybody successful pulling it into QGIS? Anybody try? Did you pull it into QGIS? Okay, you got it. Does it look just like this? Okay. Does this tell you anything? Well, sort of. Okay. Well, let's look at the layer names first. So if you click on the little arrow next to each one of these files, you can tell what the product is. Okay, so the one that there are several products that are in here. Okay. The second product is the composite latent heat value. The third product is this composite potential evapotranspiration. Okay, so it's the potential ET, that's not ET. That's the potential. Okay, the last one, we'll go down a little bit more. So this last one is the 8-day composite evapotranspiration. That's actual ET. Okay. So if you highlight that, you can change the color bar on that. Change the color bar on that, would you? Change it to a nice green color bar. Green. Okay. Green. So we're changing this to kind of a green color bar, and then change that max value to like 300 or something. 300, 200, 300. Okay. Okay, so this is the ET value. This is the ET product from MODIS. Now, the difference between MODIS and Landsat. MODIS gets you broader area ET. It's not high resolution. Okay, we're talking, kilometer resolution roughly, kilometer or less resolution. Okay, if you want to look at very small areas, very small agricultural fields, you'll have to get the Landsat product, the Landsat ET product, and not the MODIS ET product, because those really high resolution products that we're looking at from Merit and from Alexi, they have Landsat data in them. Okay, so that's the difference between MODIS and Landsat, is that resolution. Okay, so this is how you get ET into your GIS system to use it for some sort of support.